So today I'm going to start PyTorch series. This series is not going to be comprehensive about PyTorch, but when I build some end-to-end applications, the elements that are discussed here will serve as basics for those videos. So if you want a comprehensive videos, I think you should check out other videos that are available on YouTube. So let's start this particular video with the concepts of tensors. So what are tensors? These are essentially a multi-dimensional arrays that are fine-tuned to work on both CPUs and GPUs. So a scalar, for example, like 4, can be represented as zero-dimensional tensor, whereas a vector, it can be represented as a 1D tensor, and a matrix can be represented as 2D tensor, and a multi-dimensional array can be represented as a multi-dimensional tensor, right? So as we discussed, the salient features are they are good for unified data representation, so because it represents some multi-dimensional arrays, and they are efficient in computation because they work both on CPU and GPU and optimized for calculating algebraic operations. And you can also compute things like gradients and computational graphs, which we will look in next part of the video. But in this particular one, we are going to look at these particular elements: how to create tensors, what are tensor attributes, tensor operations, and reshaping tensors, and so on. So if you know numpy, if you know arrays, I think this is not very different from it. It just the way you use it changes slightly, but otherwise the numpy arrays manipulations and the tensor manipulations are very similar. So in this case, I gave one array and I'm saying torch.tensor, and x is a tensor now. And when you print it x, you can see that this shows this way. You can also create a zero subdimensions 2 and 3. So this will be a matrix of zeros. You can see here 2 rows and 3 columns. Again, if you want to create a random tensor, so you can say ran.2, 3. So it says 2 rows and 3 columns, and will create a default value. So these are all tensors. Again, it's like a numpy array, very similar. So if you want to look at few attributes of this particular tensor, you can print the shape of the tensor, you can print the data type, as well as the device that this tensor resides in. So here I have printed using x.shape, x.dtype, and x.device. And tensor operations, like in numpy, you can easily do. Like for example, here I created a single dimensional arrays. You can call z is equal to x plus y. You can do element wise by using star, and then you can do matrix multiplication. Here I have a 2 by 3 random tensor and 3 by 2 random tensor. You can use mat mul, and then you can multiply this exponent by 2 to create z. You can see the results as shown here. So another concept that's often used is reshaping tensors. So you can reshape using x.view. So it's a 2 by 3 dimension. You can change it to 3 by 2. You can, or you can change it to 1 dimensional array. So in this case, this is 3 rows and 2 columns, and here you are reshaping to 1 dimensional from 2 dimensions, and you're essentially saying x.view minus 1, and then you can see it created this 1 dimensional one dimensional tensor. So if you want to move between, if there is a GPU available, then you can print what device it is stored right now. You can say x.device, and it will print you whether it's a CPU or GPU. If you want to move to a GPU, you can simply say x to and CUDA, it will move to GPU. If you want to move back to CPU, you can say x dot to CPU. I don't have a GPU in this, so I'm only using CPU, so that's why I did not print any values here. Again, you can convert between PyTorch and numpy by simply saying a tensor can be created like using torch.rand, and then you can convert to numpy by saying x.numpy, and you can print the array type, and you can see it's a multi-dimensional array for numpy. And similarly, from numpy you can convert to PyTorch using from numpy, and then you can give x np, so you can go between PyTorch and numpy easily. So this is one concept, automatic differentiation. I will just show you the code and how to write it, but I will make a video after this one, part 2, where I will explain what automatic differentiation is, why do we need it, and how it is used in back propagation, and what is a computational graph. All of those will be discussed in next video. So if you have a tensor, and we often give this requires grad is equal to true. What it means that you can actually compute gradient of this particular variable with respect to some other final output that you are expecting. For example, in this case, you have a function of x, which is y, as 3x squared plus 2. When you say y dot backward, you can compute the gradient, which is dy by dx, by just saying x dot grad. So if you say required grad is equal to false, you cannot compute this one. Whereas if you say required grad is equal to true, you can compute this one. By default, this is true. So here I'm explicitly specifying it, and here what I did was at x values like 1. So I'm saying once like this particular x. So it's computing 1 1 1, and it's computing what happens when x becomes 1, and I'm computing the derivative of when I say y dot backward. So the result will be, so the derivative 6x is the result. So when you have 1 1 1 is plugged in, you get 6, 12 and 18. So that's what you get based on the 6x, right? So you have 1 2 and 3, so you have so what happens here is you are creating a torch tensor and saying required grad is equal to true, and then you have a function y is equal to 3x squared plus 2. So when you say y dot backward, so it will compute the gradient of this one. It will compute dy by dx, right? So if you want to print with respect to x, then you can say x dot grad and it will print the values. So I'll go in detail about this one in a later slide. So far we looked at tensors, few operations on tensors, how to create tensors, what are tensor attributes, and some operations, and how to reshape tensors, and how to move between CPU and GPU, and also looked at how to convert between PyTorch and NumPy. Let's also look a little bit detail in what the differences between tensors and NumPy. As you know, both of them can be used for the purpose of doing matrix operations on large data sets. However, tensor gives a little bit more functionality. Tensors can work on both CPUs and GPUs, and there is a important function known as autograd or auto differentiation, which is offered by default in PyTorch, and its tensors are integrated with PyTorch, deep neural network libraries, as well as TensorFlow libraries. Now, tensors are optimized for distributed computing. The elements within the tensors are not immutable. Unlike lazy execution, tensors offer eager execution. I think TensorFlow 1.1 was lazy evaluation, but I think Tensor 2.0 is eager execution. PyTorch tensors were always eager execution. So let's understand one more important feature, which is automatic differentiation. So there are this is one of the useful function in neural networks. I will go in a little bit of detail. Let me show you a couple of examples on how that is invoked in the code, and let's try to understand why this is needed for deep neural networks. So for example, here I created a tensor and I said requires grad is equal to true. So I'm essentially saying I need gradients to be computed. Let's say there is a function y, and that is just squaring this, and when we say y dot backward, it will compute x dot grad. So in this case, x grad will be, so differentiation of dy by dx will be 2x, and x is equal to 2, so 2 times 2 will be 4. That's what we have. So in this case, you have a vector instead of a single value, and here I'm creating a little bit more complicated function y is equal to 3x square. If I do the same thing, y is equal to pax, and I'm initializing with these x values of 1, which means I'm differentiating y with respect to x, where x will be 1 1 1, right? So if I try to print, the result will be 6 12 and 18. So this is a little bit more involved, so I will go through this after going through some explanation about why we are computing gradients and what is the need for computing gradients in PyTorch. So let's understand a couple of things about cost functions. So you have a model that let's say hypothesis model is theta naught plus theta plus 1. The parameters here theta 1 and theta, and we usually construct a cost function. In this case, we are averaging the difference between what is predicted by our hypothesis and what is the true value, and here we are scaling the difference and taking the average of it. So it's essentially a mean square error. You could have absolute difference, or you could have square root of mean square error as cost functions. So there can be several cost functions, but here we defined one of the cost functions, and what we are trying to do, our goal is to minimize. You find theta naught and theta 1, so that this cost function is minimized, right? So the whole learning is about finding appropriate theta 1 and theta naught. So, and it's the same thing for logistic regression. So here the same for every loss of for each example can be considered as a cost h theta and x minus y, and the whole cost function can represent the average of cost, and then the cost for a logistic regression can be expressed in this way. So this form has a convex function, and it is easy to work through gradient descent. So that's why we are not using mean square error, but this type of loss function. So in any case, if you think of a cost function, you're seeing a curvature between theta naught and theta 1. Our goal is to identify appropriate theta naught and theta 1 that where the cost is low. So how do we go about achieving that? Let's look at an example. So let's start with a simple example where I have my cost function as w1, w2, w3 as w1 plus w2 times w3, and the whole thing multiplied by 3. So this is my cost function. So how do I approach finding these w1s? Is essentially I'll start with the random values. So for w1 I'll choose some random value, w2 choose some random value 3, and then initialize with some random value, right? Initialize with random values. Then after the first then the way we update each of these weights is we start with this random value, and then we have a learning parameter, and we are going to move in the direction of the gradient. This is the dw1. So this dw1 is essentially dw1 is equal to dj by This is a gradient. So the same thing we will do for W2 minus alpha dW2 . So again, so dW2 is dj by dW2, dW3 is equal to, it's not easy to write this pen. So the question is, how do you compute dW1, dW2 and dW3 in the code, right? So this is this computation of dW1, dW2, dW3, they are computed in back propagation step. And PyTorch and computers generally use what is known as computational graph. So let's look at what is this computational graph. For this particular function, 3 times w, so the computational graph can be constructed as w1, w2, 3. Take this one and you say, let's say u is equal to times w3, and you combine this and you say v is equal to u plus w1 and j is equal to 3 times v1. So this is how you construct a computational graph, and now it's easy to compute. Let's say you have values, w1 is equal to 5, w2 is equal to, let's say, 3, and w2 is equal to 3. Let's say this is what the values are. So you can see here, this will be 6, and this will be 5 plus 6, 11, and this will be 33. So this is forward calculation. And then you can also compute a few things like, sorry, this is v. So what is dj by dv? So the differentiation is 3, and here you can compute what is dv by du. So it's 1, and also dv by dw1 is equal to 1, and here you can compute du by dw2, which is w3, and also du by dw3 is equal to w2. So these are all the things that can be computed here, but what we are interested is dj by dw1 and dj by dw2 and dj by dw3. So what we can do here, let's see how we can compute dw1, which is dj by dw1. Using a chain rule, we can compute it as dj by dv times dv by dw1. So this we already know, which is 3, and this also we already know from here, it's 1. So is equal to 3. And then how about dw2? Let's see, dj by dw2 is equal to dj by dv, dv by du, du by dw2. So we know dj by dv is equal to 3, and this is 1 from here, right? 3 and 1, and then this one we already know it as w3, which we computed here. So this one is 3 times w3, and dw3 is dj. Using a chain rule, we can do what we did before, dv by du times du by dw3. So this one is 3, and this one is 1, and this one is w2. So this is w2. So if you want to evaluate when w is 5, so dw1 is still 3, and when w2 is 3, so for dw2 is going to be 3 times w3, which is 3 times 2, 6, comma, and then 3 times w2 is dw3. This is going to be 3 times w2 is going to be 3, so it's 9. So we completed dw1, dw2 and dw3 here. So this is the usefulness of back propagation, and we can do apply chain rule to compute these gradients. So what does this mean? What is this dj by dw1 means? So it's essentially asking, if we change w by a little bit, how much dj will change. Let's look at what happens when we change w by certain things. So we know if we change w by, let's say, 0.001, this will become 11.001, right? So if we change w1 by 0.001, in this graph we will change to 11.001, and j is 3 times v, so j will change to 33.003, which means for change for little bit of change in w1, this 3 times that much amount is going to, that's why dj by dw1 is always equal to 3. So that's what it means, dj by dw1 means. So if a small change in dw1, how much dj will change, and it's 3. So that's what it refers here, and we will go back and substitute. So w1 minus alpha, which is the learning rate, and whatever dw we computed based on the initialization value, we are going to change w1 to this value. This is going to be new w1, right? So this is what we are doing, and same thing will be applied for w2 and w3. So this is the reason why this autograd function. So in PyTorch, when you say autograd is equal to true, it is actually keeping track of all of this this chain, and it's retaining the values. So automatically when you say j dot backwards, it's actually computing w1 grad, w2 grad and w3 grad. So remember that dw1 is w1 dot grad in PyTorch, and dw2 is dw2 dot grad, and dw3 is w3 dot grad, and j is our cost function. So let's see how this can be done in PyTorch. So what we did here is we are initializing our tensors. w1 is equal to 5, w2 is equal to 3, and w3 is equal to 2, and we're defining our cost function as 3 times w1 plus w2 plus w3, and here we are saying j dot backward. So because we are saying required grad is equal to true for each of these variables, Now you can compute w1.grad and w2.grad and w2grad. So you can see that we got the same results as 3, 6 and 9 in our derivation, 3, 6 and 9. So we got exactly the same values. So you can look at other simpler examples here with one variable y is equal to x square, and you're essentially saying y dot backward and computing x grad, and here 3x square plus 2. Here you have a vector instead of a single value. The result is the same thing. You get value for each of these when you say x dot grad. So with this one I wrap up this video. We looked at what cost functions are and what is a gradient descent. Essentially we are trying to find appropriate theta naught and theta 1. So let's see what is the goal of the deep neural networks is actually to learn these weights. As soon as you learn these weights, you essentially can now compute the whole function that you have defined here. So the goal of deep neural networks is to learn weights. So these are the weights that minimizes the cost functions, whether it's a simple network like this or slightly more complicated or very deep neural networks. Our goal is to compute these weights. So the way we do is we do a forward pass and compute loss, and we are going to do a backward pass and compute the gradients, how much each of those weights should be updated each time until there is no more updates in those weights. So this is a process of computing weights for a given neural network. So in this particular video we also looked at an example where a cost function was defined as 3 times w1 w3, and our goal was to compute w1 and w2 w3, which can be updated as w1 minus alpha dw1. Initially we will initialize with random values, and then we are keep on updating until our cost function is minimum. Right, so how the code does this internally is using what is known as computational graph, and this is an example computational graph for this particular cost function, where you have w1 w3, intermediately we have u and v's, and you can compute derivative of intermediate values, and using chain rule you can compute dw1 dw2 and dw3. And we also looked at how to do the same thing within the code. Here is an example for doing that, where you can define the function. Each of these tensors w1 w3 w3, which are the tensors and also the parameters, you are going to specify requires grads is equal to true, and then you are saying g dot backward, and you're printing the derivatives by using the function w1 dot grad and w3 dot grad. So with this we conclude this particular video. So far in this video we looked at tensors, PyTorch tensors, how to create them, what are their attributes and order operations are there, and then differences between PyTorch tensor and numpy multidimensional array. And also we looked in detail about automatic differentiations in PyTorch and how computational graphs help us to compute derivatives. So in this particular section we are going to look into cost functions and optimizers. First we'll start with cost functions, and we will see the intuition behind developing cost functions with an example. So let's start with a data set. Let's say we have a housing data set, and we can represent succinctly as example. If you expand on this one, so if you expand it, there are n samples, and then you can, where x1 is a vector, for example, you can have, let's say there are v attributes, and then the first one could be number of bedrooms, number of bathrooms, the square feet, and so on. And then y is a single value, it could be the price of the house. So let's assume that there is a model, like a world model, that is generating these x and y, and what we are trying to do is to build a a neural network model that can predict y given x, right? So that the choice of neural network model is up to us. We can choose a very deep neural network, or a two-dimensional neural network, or a convolutional neural network, or so on, depending on the type of the problem. Based on our experience, we can choose what kind of neural network model is appropriate. But what we are interested with once a neural network model is chosen, we are interested in learning weights. So when we say learning a model, essentially we are saying how are we learning weights. So what are these weights? Let's look into a small example and understand the relationship between neural network model, weight, and objective function. So let's start with a simple neural network where we have three input layers, two hidden layers, and then followed by one output layer. So we consider them as some default activation. We don't have to go into that, but you can see that there are weights here, 6 weights here and 2 here, so total overall 8. So the goal of learning with this data set is to understand what are the weights that will minimize, that will compute y, so that y minus y hat on average for all of the data sets, if you have n samples, is minimum. So what should be the y w's, so that the sum of all of these is minimum. So this is one type of a cost function. You can say mean square error cost function. So our goal is to, but once we construct a objective function, we are limiting the values of w's. So the goal is to learn w1, w2, and w8 here, such that this MSE is minimum. The process of building, or you can say this particular equation is a cost function. Technically, you can go through all possible values of w's, minus infinity to infinity for each of them, and then you can derive at this, but that's a very long process. And so we construct a cost function so that the derivation of these weights becomes easy. Let's look at a simple example of two variables cost function. Let's say j1 and j2. There are two weights that we are trying to learn. So if you try to build so for the regression, let's say for the regression problem, if we want to build a cost function for two weights w1 and w2, it can look something like this. So we have various values of w1 and w2 and corresponding j value. So you could start out at one of these places, and our goal is to find w1s and w2. For example, in this case, j is minimum at this point for this w1 and this w2 values. So this construction of this function is our objective function or cost function. So for different kinds of problems, for example, regression problem, MSE is best suited for a binary classification. There is a binary class function, and for a multi-label classification, there is a cross entropy and so on. Let's look at those in code. So in PyTorch, there are few cost functions that we can use by calling nn dot, and then you can call the corresponding objective function. We'll look at in which situations to use what kind of cost functions. So here I listed 6 of them. So for regression problems, you would like to use MSE loss, and for a binary classification, you want to use binary cross entropy loss, BCE loss, And if you have something like a maximum margin classification problem, you want to use hinge loss or hinge embedding loss. I think I should have changed this one to hinge embedding loss. And for a multi-class classification, you want to use cross entropy loss. And then for when your outputs or the last final layer has a log final layer is log softmax function, then your outputs will be in the log probability. In that case, the best approach is to use NL loss function. And if you have if you want to just compute the difference between y minus y hat absolute value, which is the case in forecasting problems, then you can use L1 loss function. So the code is simple. You have to call a criteria, you call that particular function, and then you call loss is equal to criteria, and then you give what are the expected output and the target, and that way it will try to minimize the difference and compute the corresponding W's. So here is a description of those cost functions, which I will not go in detail. You can pause and read this. So the code for functions for regression problems, MSE loss, for multi-level classification and cross entropy loss, for binary class NPC loss. And when you're in the last layer, if you're using a softmax, then you want to the output layer is only dimension of 1, then you want to use NL loss, and the output of from this layer is going to be the output, and the target is same, except for this one everything has the same structure of you define a criteria and you're specifying output and target. So now let's look at optimizers and the intuition behind using optimizers. So we are going to look at a couple of optimizer functions. One of them is gradient descent, stochastic gradient descent, and SGD with momentum, and briefly look at what RMSProp equation looks like. And others I think you can look into Andrew and Ju course. The course numbers are specified here for better detail. Here I'm going, mostly my focus is on understanding some intuition behind these optimizer functions and the code to use optimizer functions. So the intuition is very simple. So let's say you have a data set X and Y, and you have a neural network architecture, and you want to learn this particular parameters for that architecture that minimizes the cost function. So in doing that, we are going to construct a cost function and also going to compute derivatives at each of these locations, and we are trying to move towards the location where the cost function is minimum. We are trying to, at that point, we learned our parameters W1 and W2 and so on. So the goal is we are trying to minimize or come to a W1s by following this equation, and we will repeat this process until the difference between old value and new value is very small, 10 power minus 6 for example, or 10, and alpha is a learning parameter. So how do we go about doing this? We will look into that now. For example, so you can compute DW1. How do you compute DW1? You can go through all of the examples. For example, if your sample has 10,000 examples, then you will go through all of the examples, compute the difference between y and y hat, and average it out, and then propagate back, right? So that so if your one pass of all of the examples is known as epoch. For example, if you have 200 epochs, each time you're passing through all of the examples and you are computing DW1 and DW2, which is a decent method, but it is very slow. The lead towards coming to the globally minimum is straightforward and smooth, but it is very slow. So instead of going through all of these examples, why can't we just pass one example, compute the gradient, and then adjust all the derivatives, right? So that is another way of doing it. But what happens is that if you get an extreme y minus y hat value, you might actually push your dw's to a longer distance from the minimal point. So with this approach of using one example, you are going to have a lot of fluctuation. So we can take a compromise and do what is known as mini batch gradient, in which case, instead of using all of the examples or one example at a time, you're going to use something like a 256 examples at a time or 512 examples at a time, and then compute the gradient at that time and move in the direction of a global minimum, which is better than both of these approaches. But we can still do better than mini batch gradient, where momentum is one of the ideas. So what happens is, like, if you are computing these gradients, let's say a few hundred times, while you are coming to a global minimum, so you can plot dw1s, for example, across the iterations. So, right, so you have many batches, like batch 1, batch 2, batch 3, and batch, let's say 1000. Your derivative is going in many directions, right? So this is still fluctuating. So instead of using this derivative at this particular batch point, why can't we just average it out? For example, here this is an example chosen from like time series exponential smoothing average is what we call, where you're using your previous values and trying to keep it in the fluctuation minimum. So that can be achieved by using, instead of using dw, we're going to use vdw. So what is vdw? So vdw at the initial point is 0, and at this point what you're saying is that I'm weighing my previous examples by 0.9 times, and then my current example but 1 minus beta times, let's say 0.1 times. So as you continue to do this one at a point t, what you're saying is vwt minus 1, whatever the previous value was there, times beta and 1 minus beta dw1, which means for the current value we are weighing it 0.1 times, whereas the previous values we are weighing about 0.9 times. Because we are using at every point, what happens is the closest to the previous value will have the highest weight. As you go in this direction, you will have minimum weightage of the values that are here, versus you will have a highest weightage for the values here. So that's what is happening here. So instead of updating by alpha dw derivative at this point, you're going to do a derivative exponential smoothing average. So another use your current w1 by alpha minus sdw1, and sdw1 can be derived with this formula, which is similar to the previous one, except we are using a square instead of a single value, and it found to be doing a good job. ADAM is a combination of RMSProp and momentum. I'll not go into detail with the rest of the examples, but we will go back to our notebook and look at how to code in PyTorch. So optimizers you can write as torch.optim, and then you're using various stochastic gradient function with different parameters. For example, if you use momentum, you'll get SGD with momentum. If you want to use RMSProp, you're going to use RMSProp. If you want to use autograd, you're going to use autograd, and so on. And ADAM is specified here. So with this we can conclude optimizer, and when we use a complete example, it will be easier to understand them.